So we're going to cover these 4 topics throughout this section, starting with water quality parameters, so we'll dive right in. When we're discussing water quality, when we say water quality, we're talking about those physical, chemical, and biological parameters in regard to how that water body is used. And so it's important that designated use or to understand that water quality is a relative term, depending on how that water body is intended to be used or is being used. And we'll talk a little bit more about that designated use when we talk about standards later in this section. But starting with those chemical water quality parameters, these 5 parameters are what we look at when we evaluate water quality chemistry. And we'll talk about each one in detail, starting with EC, or electric conductivity, which is just as it sounds. It's a measure of that water body's ability to conduct electricity, which is a function of the amount of total dissolved solids within that water body, which are salts, your sodium, potassium, chlorate, carbonate, sulfate, magnesium, for example. And so with a high TDS, you find a higher ability of that water body to conduct electricity. So we'll go in and take a measurement. It's measured in microsiemens per centimeter. And a high EC will indicate a high TDS. And what this tells us is generally a measure of how salty that water is, which, as we know, can determine how suitable it is for ag irrigation, municipal drinking water use, for example. And while most of these don't have any significant health risks to humans, may cause some bad taste, there are some that do, arsenic, for example. So just something to think about. pH, the second water quality parameter we look at. It's measured on a scale from 0 to 14. If you can think back to high school chemistry class, it's not long ago for some of us, maybe longer for others. A few household chemicals that we commonly find: bleach being very basic, near the 14 end. Baking soda also slightly basic. Tomato juice, beer, acid rain on the acidic side around 4. And then you have your strong acids, your battery acid, hydrofluoric acid, and then pure water falls at neutral 7. Just a few others up there. Now, we measure pH because it determines how soluble or how toxic some substances are in water. It can affect, like I said, the toxicity and how they affect wildlife, for example, or other water quality parameters that we look at. So can anyone venture a guess on what's the optimum water quality pH? If you had to put a range to it.
6, 7,
5 to 9.
I heard 5 to 9. It's close. 6, 7, 8. That's right on. 6.5 to 9 about. So judging by this chart, we say good water quality is somewhere between urine and baking soda. Easy way to remember it. Dissolved oxygen, moving on to our third parameter, is just that. It's a measure of O2, or the amount of oxygen that's dissolved in that water. There are several ways in which oxygen can be introduced into that system. Mass diffusion, for one. Our atmosphere is about 26% oxygen, as many of you may know. We have that mass diffusion coming in at the water surface. Also some aeration, that churning of that water, mixing the O2 and that air in when you have those ripples. And then you have some biological processes, photosynthesis, taking that CO2, putting off O2. However, although there are additions, there are also some ways that oxygen can leave a system as well. Decomposition of organic materials, for example. And this is an important one we'll touch base on when we talk about another parameter. But those plant materials and also fish, other wildlife, as they die and decompose and break down, they use up oxygen in that decomposition process. Also respiration. Plants, although they're giving off O2 when they're photosynthesizing at night, you do have some respiration, letting out of CO2. So just another way. Fecal bacteria. This is an indicator organism we look at. We have fecal bacteria in our intestines. They're found in the intestines of all warm-blooded animals, and we use them as an indicator to indicate the presence of that fecal bacteria, and with it commonly the potential presence of pathogens. So viral pathogens, bacterial pathogens, and also some parasitic pathogen potentially as well. Like I said, we measure fecal coliform and E. coli as the 2 primary indicators that we use here in the state. And it can be very harmful to not only our health, but also potentially health to wildlife that come into contact with that water as well. So fecal bacteria being the fourth chemical water quality parameter. Nutrients. Nitrogen and phosphorus are the two we're concerned about in this case. We find them very readily in the environment. They're essential to life, plant life, animal life. Added by us in the form of fertilizer to ag fields, our home lawns, golf courses, for example. When you find them in excessive levels, that's when you start to cause some issues, though. It can lead to a process called eutrophication, which is basically when you have an excess of nutrients, you have an excess of plant growth. And while that's good, if we remember from the DO side, they're putting oxygen back in that system, which is a good thing. That oxygen is necessary to sustain biological life. It's not sustainable. So when you have that excessive plant growth, eventually you're going to run out of nutrients, or it's not going to be able to support those plants, and they'll start to decompose. And when that happens, they're using up some of that O2, if you remember from a couple slides back. So this eutrophication can lead to a dead zone, or a zone of depleted oxygen, and basically where nothing can grow, no plant life. A lot of aquatic species won't be able to survive as well. Anyone heard of the dead zone right at the mouth of the Mississippi? The zone of eutrophication, it's also referred to. This is a result of what we're seeing. Yes, ma'am.
Can that can be corrected, and how long would it take if it was like naturally? I mean,
it's highly variable. There are ways that it can be corrected. Plants are a natural sink for it, so you will over time have those plants assimilating those nutrients. Also, stream flow. If depending on the hydrology of that stream channel or pond, you can have it flushed out downstream if you have a high rainfall event. Soil's a good filter. I mean, there are so many variables there. It's hard to put a time frame on how long it would take. But yes, it's a natural process and a very dynamic process. So over time.
You get a couple of things in a pond. You get algae and you get duckweed. Do those result in eutrophication?
If you have excessive levels, it's all in the right balance. If you start to have an excessive amount of
somehow by lowering the nitrogen or phosphorus in the pond.
I'm sorry, your question?
The nitrogen or phosphorus in the pond.
Your question is, can you lower the nitrogen?
Can you control the overgrowth of algae or duckweed?
Yeah, absolutely. If you manage your nutrient levels within that pond, as a result, you're going to manage the amount of plant life it can sustain. So that's a very good point.
Yes.
And you can determine that by taking a water quality sample and judging about how much nutrients. You do want nutrients in a pond to sustain that plant life, but at optimum levels. Say again?
What would you do to lower the nutrient level?
Well, give it time. Let those plants act as a sink. Obviously, if you have a mechanism to drain or introduce new water into that pond, sort of flush it out, if you will. There's some additives, I think, that will help for some phosphorus to help it settle out and bind to that sediment there. But generally, time is the best measure.
Thank you.
We're going to touch really briefly on the physical parameters. These four are the ones we look at. Temperature. It can affect the biological processes, once again, the rate of chemical processes as well, some of the stuff we've just talked about. DO, for example, cold water can hold more dissolved oxygen than warm water. Just an example there. Total suspended solids. This differs from total dissolved solids, and this deals with solids that can be trapped by a filter. So your sand, silt, clay, organic material, sewage, for example, is what we're talking about when we say total suspended solids. When you have high total suspended solids, it can also in turn affect your temperature. When you have that large amount of sediment there, you tend to see a higher temperature in that stream bed, which can affect, like I said, biological processes and chemical processes alike. Turbidity, which is a measure of how much light passes through that water body. So if you have a lot of sediment in that water body, you're going to have a very high turbidity, not a lot of light passing through there. Doesn't go very well for submerged aquatic vegetation that rely on that sunlight for photosynthesis, for example. And lastly, stream flow. governs everything, chemical, physical, biological processes alike, the amount of water you have flowing through that stream, lake, river, water body, and the rate at which it does, the frequency, for example. You may have heard the phrase, dilution is the solution to pollution. Anyone heard that before? It's not an absolute, it's kind of a funny saying, but that's what it speaks to, is that stream flow and hydrology is paramount in affecting your water quality and those parameters we've just talked about. So lastly, biological parameters, just to touch base briefly, often referred to as Browell criteria, and this is simply just looking at the aquatic life in there, the submerged aquatic vegetation, some of your fish and macroinvertebrates as an indicator of how healthy that water body is. So if you see healthy populations, it could be an indicator of good water quality. And benthic macroinvertebrates is one category of organisms we typically look at. What that means, it's a big word. Benthic meaning bottom dwelling, macro meaning large enough to see with the naked eye, and invertebrate, of course, meaning having no backbone. And while you may be thinking politicians, no, this is still a aquatic species we're talking about here. Biological oxygen demand, just looking at the amount of oxygen being used up in that system. If you have a lot of decomposition, you're going to be using up a lot of oxygen. This is simply a measure of that to potentially indicate some other water quality issues. And submerged aquatic vegetation. Often good it is good to have. It's photosynthesizing, providing habitat for wildlife. So if you see that aquatic vegetation dying off or not present at all, that could also be an indicator of poor water quality. So here in Texas, we have a few maps up. Bacteria and dissolved oxygen are the two main pollutants we see here in the state. A few toxicity impairments, pH and dissolved solids, but by far the largest two are bacteria and DO. We find most of the impairments in the eastern side of the state. Anyone care to venture a guess why? Are they just really good at managing water over here in West Texas, or are y'all just really bad? Or help me out here.
Nobody lives there.
Y'all a good group, man. Y'all hit both of the points I was going to make right on the head. This is where the water at. We have more rainfall over here, obviously, than the western side of the state, and people. Most of our population lives within that Texas triangle, or east of I-35, if you will. And you get people and water together, you tend to have some water quality issues. That's just the fact of it. So a couple things going on here, but what you can take away from this map is most of our population rainfall occurs in the eastern side of the state, and as such, that's where we find most of our impaired water bodies. Specifically here in Lake Livingston, the Trinity River upstream has been impaired since 2010 for dioxin and PCBs. Lake Livingston itself since 2006 for elevated levels of sulfate and for a pH issue.
Is there any mercury in the history?
I don't know. There very well may be. So some segments are listed for parameters and then delisted, sometimes due to management measures by us.
I don't know.
It's mainly in the northern sections. You don't see it so much because the water gets so diluted by the time it gets down to us. So up towards the Dallas-Fort Worth area, they do have mercury issues, but down in this area we do not. Thank
you. So that was a very broad overview of water quality and the parameters we look at to measure water quality. We're going to move on and talk about some sources of pollution that can contribute to elevated levels of some of those parameters or poor water quality. So if you had to put one word to it, what would cause those chemical, physical, and biological parameters to become impaired? Starts with a P, ends in lution, pollution. These aren't trick questions, folks. These are simple. Pollution's the answer, and we define or categorize two types of pollution. Point source being the first, which is pollution simply that comes from a defined or discrete source. I like to think of it, if you can point at it and tell me where it's coming from, it's a point source. So examples of these would be a pipe or a ditch or a stormwater outfall. And then you have non-point source pollution, which, as the name implies, doesn't come from a defined or discrete source, but rather from sources spread out across the landscape. So areas like urban areas, agriculture, industry, you name the sources, just basically everything that's not a point source is a non-point source. It's spread out and from a number of different sources. So all of our river basins, coastal basins, the estuaries here in Texas are affected to some degree by both point and non-point source pollution. Which do you think is bigger or has a bigger impact on water quality issues here in the state? Point or non-point? Non-point. That's exactly right. About 92% of the impaired water bodies are affected by non-point source, so the vast majority. That being said, we're going to spend most of the time in this section kind of reflecting. We're going to touch very briefly on the types of non-point source pollution, but just to wrap up point source, here are a few examples. Animal feeding operations are considered to be point sources. Industry discharge, municipal wastewater treatment plants, and also stormwater outfalls are all managed and considered to be in the state point source discharges. Non-point source pollution, we have 4 types or 4 categories, if you will. Fecal bacteria, which we talked about. Nutrients, sediment, and lastly toxic and hazardous substances. And this last one we haven't really touched on, but this deals with your petroleum products, cleaners, solvents, pharmaceuticals, pesticides, herbicides, fungicides, all those chemicals that we use so readily around the home, business, agriculture, for a number of reasons. And there are a lot of human activities, human areas that can contribute to these water quality issues or add some of these pollutants into these watersheds. Just to name a few, this is a very basic map, but just to kind of put in your head how human activity can have an impact on water quality. Urban runoff, for example, faulty landfills, discharge from there. Faulty septic systems. Here in the state, I think it's estimated 1 in 6 septic systems is expected to fail at some point in its lifetime, so around 17%. Obviously an issue in some watersheds. Pesticide, fertilizer, when it's applied in excess to ag fields or golf courses or home lawns, for example. If it's used in excess or applied improperly, there does exist that potential for it to find its way into a water body. Manure from livestock. And there are a whole plethora of human activities that can contribute. It's important to note that there are some natural additives as well. Wildlife can contribute, natural processes and functions. So it's not just us, but it's important to recognize that the stuff that we're doing, especially as we're expanding our urban areas and our population's growing, it's important to realize that we're having an impact as well. And so when we're looking at addressing water quality issues, we want to address not only the natural side of things, but our activities as well. So moving on and talking about consequences when we find impaired water bodies or impaired water segments. We took this photo actually just north of Lake Livingston last week. We can really summarize or categorize the impacts of poor water quality in 3 categories. Economic consequences to biodiversity and the environment, and lastly, most importantly, to human health. So we literally spend millions every year to control, remediate, and prevent non-point source pollution and point source pollution from entering our waterways and once it does enter our waterways. Very expensive. It's a lot cheaper to control pollution before it gets in there than it is to try to remediate, mitigate after it's already made its way into that system, that water system. These are complex, dynamic systems, and once it's there, some of these pollutants can be very persistent in the environment. And where does the money for this stuff come from? Taxpayer dollars, right? Our pockets. So it's literally financially in our best interest as taxpayers to try to address these issues before they become worse issues, before they become a problem to begin with. Biodiversity, pollution can destroy valuable habitat. By so doing, it can lead to the removal of some desirable species. Fish species, for example, submerged aquatic vegetation we talked about, and in turn can lead to the establishment of some undesirable species as well. Human health and happiness, we talked about bacteria being an indicator organism. Contaminated water, it's an indicator organism for the potential presence of pathogens, right? So that bacteria, viral pathogen, parasites, which can cause a whole host of ailments, and I'm not going to name all of these wonderful things listed here behind me, But you get the point. That bacteria in there and other chemicals, toxic and hazardous substances can have a very detrimental effect on our health if we come into contact with it, whether it be as a drinking water supply or in a form of recreation, swimming, boating, for example, but also to wildlife health as well, if they're using that as a drinking water source or, you know, otherwise using it to cool off or however they are. And lastly, human happiness. We use these water bodies as a source of recreation, fishing, boating. Any fishermen in the audience other than myself? I'm the only one here. Well, I like to fish, and if I couldn't, due to impairments in the river on that lake, I mean, it would affect my lifestyle and, you know, in turn, my happiness. So another consequence to think about is how we use these water bodies, not just to survive, but also to recreate and in our everyday lives, or at least on the weekend lives. So, and to wrap up this section, I wanted to touch a little bit on some of the water quality law here in Texas and management. Yes, ma'am.
I was curious, do they test, take fish samples from some of these bodies of water and test them for how safe they are to eat?
Absolutely. And what they were talking about is mercury impairments in some of the northern ends of the Trinity. That's what they're actually testing is the level of mercury in edible fish tissue. So what they will do is go in and take samples of species that are commonly consumed by us, you know, so your bass and catfish, and they'll test the mercury levels in that tissue, and they have a threshold for that. So when we say that a water body is impaired from mercury, it's impaired primarily in the tissue of those organisms that are commonly consumed by us.
So then they say, do not eat the fish here?
Exactly. And they'll, you know, do things like,
mainly mercury and not other things?
when they do those fish samples, they'll test for not only mercury, but other chemicals as well. I mean, I don't know, the PCBs, dioxins. Are there any others other than the main three?
They do metals in general.
Heavy metals. Okay, so it's very heavily regulated. It's a human health concern, and as such, there's a lot of effort that goes into that. But as we've heard, there's a range of tests that's conducted on that fish tissue. So
it's managed by the Department of State Health Services. Actually, it's the ones that actually issue the advisory.
That you should fish, but return them on.
Right. Or don't consume more than X
some
amount. Sometimes it's very limited quantities are okay, but not in excess of whatever they advise.
Thank you. Sorry.
no, they're great questions. Keep them coming, please. So just to wrap up this section, as I was saying, I just wanted to touch base on some of the governing law and policy here in Texas and how we manage for water quality, and a few of the agencies at play. And so to start, I just wanted to point out that there are a whole host of agencies at all levels, the federal, state, and here locally, that have roles or responsibilities when managing for water quality. And of course, we all know the main player at the federal level, the US EPA, right? Their regional headquarters up there in Dallas, just up the way. But there's also a couple other federal agencies as well that serve roles, the United States Geologic Service and the Fish and Wildlife Service as well. Here in the state, the two primary players, which we'll talk about here in the next couple of slides, are the TCQ and the Texas State and Soil and Water Conservation Board, this acronym here. And I'll talk about these two specifically next. But the Water Development Board and Parks and Wildlife Department and the General Land Office also are players as well. And then you have your regional players like the Trinity River Authority. We have a couple representatives here today. Water Conservation District, Groundwater Conservation District, Council of Government, for example, and then you have those local entities, municipalities, nonprofit organizations, water suppliers as well. So while there are a lot, the idea being is just to give you a sense of how broad of a scope it is when we're talking about people at the table, players at the table. There are a lot of agencies that have roles to play or that can contribute when we start to look at managing for these water quality issues in these watersheds. So the first, the primary water quality management agency here in Texas is the Texas Commission on Environmental Quality, or TCQ, TSEC as they're sometimes abbreviated. They are the primary water quality agency here in Texas. They plan how we use these water bodies and how we manage for water quality. They issue permits for the point source dischargers that we talked about, so those industrial dischargers, stormwater discharge. They're the ones who regulate those permits. And they also regulate programs for urban non-point source runoff as well.
Are they partnering with you in the Trinity Water Program?
That's a question for Blake.
At the present time, we really haven't been involved with TCEQ since they do point source pollution mostly. We work primarily with the Texas State Soil and Water Conservation Board, which he's actually going to talk about right now. That they focus on non-point source pollution.
Which that's right. As Blake just mentioned, where TCEQ has the urban non-point source side of things and the point source, the Texas State Soil and Water Conservation Board has a mandate to administer the state soil and water conservation laws, and in turn, as part of that, manage programs to help prevent non-point source pollution from agricultural sources and forestry sources or silvicultural. So you have TCEQ doing urban and point source, and then State Soil and Water Conservation Board doing non-point source from ag and from forestry in rural areas, basically. Make sense? So the laws that they administer and govern primarily deal with surface water quality and drinking water quality. And diving into some federal legislation, the first piece of federal legislation that came about that dealt with surface water quality was the Federal Water Pollution Act of 1948. This primarily dealt with industrial and municipal wastewater issues, discharge issues, and it didn't have a whole lot of teeth to it, but it was a start. It was significant in that it was the first piece of legislation that came about. So it's been amended several times since then to become what, as we know today, is the Clean Water Act. The most significant amendments taking place in 1972 and 1977. It's basically the foundation for the surface water quality standards that we have here in the state and in the nation. Mandate to restore and maintain those chemical, physical, and biological properties, that water quality we talked about. And also requires states to set standards for surface water quality, which I will talk about how TCEQ evaluates and sets those standards here next. And it's important to mention that while this is a federal piece of legislation, EPA, as they often do to most states, will delegate that responsibility to a responsible state entity, in this case our TCEQ. So they have responsibility for fulfilling the mandates set forth by that Clean Water Act of 1972 and 1977. So those standards primarily deal with surface water, wastewater, but we also do have standards for drinking water through a different act, the Safe Drinking Water Act, Federal Safe Drinking Water Act, FSDWA. Got that right? If you haven't noticed by now, here in the water quality arena, we like our acronyms, as many government people do.